Welcome. Today's notes worksheet is entitled Linear Models. We'll be taking a graphing calculator approach to linear functions today, so please make sure you do have your graphing calculator available. And I'll try to walk you through some of the steps and some of the buttons that you press. And what we'll pretty much do is just analyze some data and allow the calculator to come up with a linear model in that y equals mx plus b form, and then we'll go ahead and utilize it in some way, shape, or form. So let's do a couple things at the top here to get us started before looking at our first data set. There are a couple preliminary steps that we're going to have to accomplish here. One of these we will go ahead and just do, and you won't have to do it again. So let me bring my calculator up, and then let's go ahead and give this a try. So first order of business, I need you actually to press the second button for me, and then the number 0, that's the catalog. And then just work your way down as best as possible there. I'm going to work my way down into the D's. And again, this is something that we're just going to do. Unless it gets reset, you really don't have to do this again. Just one time only. Go until you see diagnostic on. There it is right there. So go ahead and hit diagnostic on, and then enter. And it should just say done like mine. And this just allows some of the data that we're going to want today to appear. And so, again, once we do this, we're good to go. We don't have to keep doing this every time we have a scatter plot to work with. All right, now a couple of preliminary steps that I have on your sheet here. Let's go ahead and take care of these pieces. So I do need you to press the y equals button here at the top. And if you have any equations in here, if you can just clear those out, that would be great. Now the second order of business, after you've cleared out any equations in the y equals, is to turn our scatter plot on. And there are a couple ways to do this. I'm going to show you the efficient way right off the bat here, but then the less efficient but more necessary way, I guess, in just a moment here. So here's what I'm going to do. Do you see up here plot 1, plot 2, plot 3? So a quick way to just turn it on and turn it off is to just go ahead and highlight it and maybe press enter. And notice in that case now my stat plot is on. And that's good. We do want that on. So that's one way to do it. The way that I wrote on your paper right here, and I'll just kind of circle this right here, is to hit the second and then the y equals, and it gets us to this menu right here, and you have a whole bunch of different plots that are available. We're just going to do plot 1, of course. And notice my plot is on. I had just turned it on. But this is a way to kind of go into it and get in a little more detail. So in this case, it's another way for on versus off right here. So obviously I had mine on. Please make sure just that you have yours on. And then this might be different on yours at this stage, so what we need to do is highlight the scatter plot right here, so we're going to be utilizing this one. Make sure that your lists match up here. So our x's are going to go into the L1, and our y's are going to go into the L2. And then the mark, your choice, really doesn't matter. So this is a menu that you'll see if you want to really dive in and get the details taken care of for any scatter plots that you're working on. Okay, good. So preliminary stuff taken care of. I'm just going to go ahead and hit second and quit, and then just go back to the main screen. Now, anytime we're working with a set of data, and we will be doing this over the course of the entire year, I always think of it as a 3-step process. So we enter the data into the calculator, we view the data on a scatter plot, and then we allow the calculator to model the data using a particular equation. And so we're going to do exactly that piece, enter, view, and model. So let's start that process, the enter stage. And let's, I guess, first and foremost, read our data set and see what we're dealing with. So I'm going to go ahead and get rid of this, and then we'll go for it. So let's get into example 1. It says, the following table shows the calories burned per minute when walking at 3 miles per hour. So we have 2 variable quantities related together, body weight and calories burned. And so you can see, let's see, we've got 1, 2, 3, 4, 5, 6 data points relating these 2 variable quantities. And, you know, I guess before we really talk about this in a linear fashion, we should talk about it in terms of functions. In this case, what we want to think about is which would be the dependent variable and which would be the independent variable. So think about that for just a second. Again, we've got your body weight and the number of calories burned when walking 3 miles per hour. And this is per minute, it looks like. That's interesting. All right, hopefully you came up with something good. I would phrase this as the number of calories burned depends on the body weight. So in terms of the dependent variable, I'm going to write calories burned right here. And I'm just going to throw a little y on the back. Remember what we've been kind of talking about. Y depends on x. Y is a function of x. So the calories burned, I would argue, is the dependent variable. And body weight, of course, as a result, would be the independent variable. So I'll throw that in there. And being the independent variable, let's use our generic x right there. All right, very good. And you can kind of see a little pattern emerging. 100 pounds, 2.7 calories burned per minute when walking at 3 miles per hour. 120 pounds, 150, 170, 200, and 220. And so what we want to do is kind of see what the graphical pattern would be with these 6 points on the coordinate plane. And so that's exactly what we're going to do. So let's enter it into the calculator and allow the calculator to come up with a nice scatter plot. Okay, so first order of business is to enter it in. I will slow it down for a sec as we press these buttons here. I need you to find the Stat button for me, which is right there. And then as it says on your paper, we go into Edit. Now I have a nice clear set and I'm ready to go, but you might not. So here's the idea. If you have numbers in here, and notice under the L1 and L2, which is exactly what we're after, we want to clear those out. And so it says that right here, clear L1 and L2. And here's the best and easiest way how to do that. So what you're going to do is literally just go up into the L1, and you're going to hit clear and then enter. And if you do that, any of the numbers that are under that list should go away. If you have them in L2, you do the same thing. So you go up to L2, see how it's highlighted, and then I press clear, and I press enter. And notice, should be cleared out at this stage. And so we do want that cleared out, so we can go ahead and enter it in. Remember, L1 will be our x's, in this case the body weights. L2 will be the y's, and in this case the number of calories burned. So let's get that in. I'm sure you can type a heck of a lot faster than I can, but I'll get this in here, and then we'll move forward from there. So just enter after each one, that's all. Should be pretty straightforward. And 220 for me. Calculator is very, very picky if things do not match up, so please make sure all of the x's and y's match up perfectly. So ordered pairs here, 100 and 2.7. And then the 120 and the 3.2, etc. right down the line here. Let me get my remaining ones in. And then we'll take that next step. Okay, there it is. So again, enter, view, and model. And so as a result, we have all this in. Hopefully those instructions will suit you. And then we move over to this stage right here. Now what the calculator is going to do is put these ordered pairs on the coordinate plane and create a scatter plot. Now the good news is the calculator is going to pick a pretty ideal window to do this. So we're going to let it do exactly that. So notice what you do to view the data. You hit the zoom button at the top. And we've potentially seen this window before. We've probably worked with this one right here. But basically what we want to do is go on down. It should be the 9th one, so you could probably just press number 9. But basically you should see something that says zoom stat. And so that zoom stat right there should suffice. And so I'm going to go ahead and enter it. And then you notice the window that pops up here and a nice scatter plot. And I'm going to just hit window. You don't have to. But you can see what the calculator selected for the x's and the y's. So body weights, it went from 88 to 232. And you can see a little on the front end, a little on the back end there. And the calories burned went from about 2.1 to 6.4. Again, little in front, little on the back, looking great. So there's our scatter plot. And as you can see, we can really make a judgment about this that the data looks pretty linear. There is a nice linear pattern to those data points. And so what we now want to do is allow the calculator to come up with a particular linear model to best represent this data. And so that's our next piece. So let's go ahead and do that. Model the data is the key piece. So let's make sure we do this appropriately. So everyone hit Stat for me. Move it over to Calc. And you'll see a whole bunch of what are called regressions here, most of which we will see over the course of the year. Just FYI, this is the one we're going to be looking at right here, linreg, so linear regression. And it says it as ax plus b. Obviously, that a is really our slope, so mx plus b. You'll see a couple others along the way here. Here's quadratic, cubic, quartic, another linear, but we won't use that. What's called logarithmic, exponential, power, logistic, and what's called sinusoidal, so a trig function in there as well. So a variety of functions, obviously, to take a look at, and we'll get to as many of those as possible over the course of the year. Regardless, for our purposes, guys, we're talking about linear models here, so let's go ahead and highlight that one, or just hit number 4. And if you hit enter at this stage, the calculator is going to give you the y equals mx plus b, and you're going to be good to go. I'd like to do one more thing with this, and you'll notice on your paper I kind of put it in parentheses right here for us. I like pasting the model into the y equals. So I like seeing the graph in conjunction with the data points. And so here's what we're going to do. I'm going to hit the vars button, and I'm going to move it over to the y. And you notice, of course, it is a function, so I'm going to go into function. And then I'm just going to find this y1 right here. And basically now I'm telling the calculator, take this regression and paste it into the y1. Now, if you don't have a TI-83 like I do right up here, if you have a TI-84, it might look a little different. I believe on that one there should be something that says something along the lines of store equation or something like that. And where it says store equation, that's where you're going to put the y1. So you're going to follow these, this process right here, I guess, into that situation where it says, I believe, store equation. Again, if you're not sure, I'm very good at troubleshooting these, so if you have any issues with these calculators, you will, of course, let me know. All right, I think we're ready. So we're going to hit enter at this stage, linear regression into the y1, and we get that right there. So notice, of course, our mx plus b basically. Here's our slope right here. Here's our y-intercept. We'll talk about really this one right here, this little r, in just a second. So I need to go to my next screen, and then I'll bring this back up momentarily. So hang on just one sec here. There we go. And so let's see what we've done according to your paper. Use the calculator to make a scatter plot. We definitely did that. Find a linear regression for the data and round to 3 decimal places. We just did that. And so what I saw, and I have this on my sheet, I got a slope to 3 decimal places of about 0.027, so it's 0.027x, and then I got a y-intercept about negative 0.017, something along those lines right here. So check your calculator, make sure that matches up, but we placed the numbers that they gave us for the A and B into those 2 spots right there. All right. Now there was one other measurement that came up when we looked at this, and so we go to letter D on your paper, and it says the correlation coefficient. So guys, circle that if you would. So the R value is a statistic that illustrates how well the line of best fit represents the data. So the closer that the absolute value of R is to 1, the more perfect the linear relationship. And in this case, what is the correlation coefficient? So let me bring my calculator back up. There we go. And so it's this R value right here. And we'll talk about this number in a little more detail in just a second. But you see the R value is about 0.99978, somewhere in there. So I'm going to go ahead and put that in, 0.99978. And as it says, the closer that that absolute value of R is to 1, the more perfect the linear relationship. And the more confident we can be that our model represents the data well. And in this case, obviously, we can be quite confident that we have a good model for this data set. Now, just one thing to note here on this, because we're going to see all types of data sets and so forth. If we have a scatter plot that is increasing, then the R value is positive. If we have a data set that is decreasing, and so as a result the line of best fit would be a declining line, then R is negative. So I guess here's how I'm going to write it. So line of best fit, just kind of thinking off the cuff is how we want to do this. So if the line of best fit is positive, No, let's do that a little better. Hold on one sec. Let's get rid of that. There we go. So if the line of best fit is inclining, that's the best way for me to say it, then the R value is going to be positive. And that's what we saw right here, obviously, a positive R value. If the line of best fit is declining, so the data set is going down, then the R value is going to be negative. But again, if we have an R value maybe close to -1, then that's good. That means that it's quite linear. So I hope this helps to some degree. I'm just going to underline that to separate it, underline that to separate it. But I think that should suffice. It's not ideal, but it's pretty good. All right, so again, I look at that R value as a measurement of how linear our data is, and you can see our data is very linear. Now just one thing to note, and then we'll kind of move on to the next piece. I'm going to go ahead and hit the y equals, and notice I had the calculator paste in our regression, and that really looks nice. So I don't have to do it manually. The calculator did it for us. And then everyone, I'm going to hit graph right up here, and you can see the line of best fit in conjunction with the data set that we put in. And you can see it's pretty good. So some great things you can do with this calculator here. We'll go ahead and take these next couple pieces without it, but again, I kind of like that piece. All right, let's do letter E. It says, what is the meaning of the slope in the context of the problem? All right, so obviously one of the key ingredients to dealing with linear functions is understanding the nature of slope. And so why don't we go ahead and utilize the idea of slope with this particular function right here. So if you remember, slope in very basic terms would be the rate of change. Okay, and basically what we did with that formula, we talked about it as the change in y per change in x. So guys, stare at that number for just a second and look at the two variable quantities that we have, and what does this 0.027 really represent to you? Okay, think about that for a second. Maybe write something down or just have it in your mind there. What does that slope represent in relation to the problem? Again, the two variable quantities, the y's were the calories burned, and the x was the body weight. So let's try to put this into some perspective. I'm going to write down what I have on my paper, and feel free to paraphrase it to some degree. But what does that 0.027 represent? All right, enough rambling. Let's get it on there. So here's what I have. Remember, it's the change in y, and because the slope is positive, I would argue, of course, it's increase. So it's the increase in the calories burned per minute and obviously, guys, when walking at 3 miles per hour, I should put that in there, but I'm not going to. So it's the increase in the calories burned per minute when walking 3 miles an hour. Actually, I will put it in. I want to be as complete as possible. So when walking, so there's your change in y. In this case, because it's positive, it's an increase. So the increase in the calories burned per minute when walking 3 miles per hour, and we have to be careful, per change in x. And so the way I phrased it is basically for each additional pound. So it's not per pound. We have to be a little careful on that piece. It is not per pound necessarily. It's for each additional pound. So again, as your body weight increases by 1 pound, the number of calories that you burn per minute walking 3 miles per hour increases by this right here. I hope that makes pretty good sense. Change in y per change in x. And that's the idea here right here, changing the x. So try to get comfortable with that piece if you can, understanding the concept of slope. Okay, good. Let's move on to the next piece. Obviously, when we have a model, we use it to make predictions. So it says use the equation to interpolate. And everyone, if you would, can you go ahead and underline the word interpolate for me? The calories burned per minute if a person weighs 159 pounds. And I guess I would ask you this in terms of our variable quantities. Is this 159 right here, is that an x value or is that a y value? And if you look at our data set from above, body weight was x. So guys, this is an x. I'm going to throw a little x right on top of that. So keep it simple. We could use the graphing calculator here, but quite frankly, I think it's just as easy to go ahead and use the model. So I'm going to use the model here. That was kind of the whole point. So we have our slope, and in this case, we have a particular x value. And so we throw that x value into the model and use that to find the y. Given one, we find the other. Given an x here, we find the y. So I'm going to go ahead and just bring my calculator up and do this calculation, nothing more. So I'm just going to go back to my main screen and do 0.027 times 159 and then minus 0.017. And hit enter. And so you can see right there about 4.276, give or take. And if you look at the data set from above, I'm not going to do that at this stage, but if you look at that, that should probably fit in pretty well. So about 4.276. Okay, just a nice prediction, something that was not in the data set, but once we have the model, we can be pretty confident about it. All right, letter G. Use the equation to extrapolate. So underline extrapolate for me. The calories burned per minute if a person weighs 250 pounds. Okay, everyone, if you would, can you put another x on top of that? So obviously it is another body weight. So I think we're just repeating that process here. And so everyone on your paper, give me the 0.027, in this case a heavier set person. So 250 and then minus 0.017. Same deal, just given an x, you should be able to find the y. Let's bring that calculator up and do it. So I type in that, in this case 250, and then minus the 0.017. And again, it is just a prediction. And in this case, you can predict that somebody weighing 250 pounds, walking 3 miles per hour, would burn 6.733 calories per minute. All right, great. Now here's the thing. If you look back on the last two problems, I did the exact same thing, except I used two different words for it. They're both predictions. And so the question is, why did I use interpolation for the first one and extrapolation for the second one? So notice what letter H is asking. It says, what is the difference between interpolation and extrapolation? They're both predictions. I did the exact same math. So the question, of course, is why did I use two different words for it? And good vocabulary right here, inter versus extra. Think about that for a sec, and then let's see if we can make sense of it. So what is the difference between interpolation and extrapolation? Well, I hope you realize that it really all came down to the numbers. I used interpolation with a body weight of 159, and I used extrapolation for a body weight of 250 pounds. What is the primary difference between those two values? Well, if you notice, the 159 pounds was within the bounds of our data set, right? If you look at our data set, the body weight was from 100 to 220. 159 is right in there. But the 250 is outside the bounds of our data set, right? It only goes up to 220, and yet I want to make a prediction on 250 pounds. So two different words for two different types of the same prediction, I guess. So here's what I have. Interpolation is within the bounds of the data set, as I already stated. And of course, extrapolation is outside the bounds of our data set. Okay, which begs the question. And it's coming right up. Let me just get this in. Which can we be more confident with? Which is more reliable? Interpolation or extrapolation? And I think it's fairly obvious here that we would probably be more confident with our prediction when it's an interpolation thing as opposed to extrapolation. Again, interpolation is right within that data set. We can see that it fits within the pattern that we've already developed. But the 250 pounds, which is outside the data set, is really outside our bounds of knowledge, so to speak. And so we don't know if the model that we've created continues past the last data point. So sorry for rambling about this, but if you kind of look right here, 159 is somewhere in here, and we're fairly confident that that can fit within the same pattern. But 250 pounds, which is somewhere out here, it's past our last data point, and we don't know. We don't know what happens after 220 pounds. Maybe the model starts to change. Maybe the pattern differs after here. And so obviously interpolation we can be a little more confident with. Obviously most predictions are probably extrapolation. Okay, good. So that's our first data set, really talking it through completely. I think we will try to do one more here, and maybe we can split this up, like I'll do one and you do one. This is one that I came up with by myself. It's a fairly intriguing one. I won't go into too much of the history here, but I grew up as a baseball fan, and at the time, Hank Aaron was the home run king, basically. He hit the most career home runs. And so here is his kind of data set with the number of games that he's played and the number of home runs hit. Well, Barry Bonds came along in the late 90s and early 2000s, and he actually broke Hank Aaron's all-time record. It's one of the most cherished records in all of sports. And again, not to dive too deeply into this, but there was a lot of controversy about Barry breaking the record, as a lot of people had considered him to have taken steroids. Again, we won't go there. It's never been proven apparently, and that's fine. But I was curious, just in terms of a linear model perspective, if there was kind of a change in sort of the pre-steroids and the post-steroids if Barry Bonds had taken them. And so I was curious if there was kind of a change in the pace that Barry Bonds hit home runs and how that compared to Hank Aaron. So try to make a long story short there. Okay, so let's go ahead and put this in, and then we'll see what we have. So the number of games played, I had to kind of do this in a couple different lines. So this is the games, this is the home runs hit. Continuation of the games, home runs hit. So that's all for Barry. And then same down here, games, home runs hit. Games, and home runs hit. And so again, I was just curious if there was some type of discrepancy when Barry started really hitting some home runs at a quick pace compared to Hank, and who would be the better home run hitter, basically, is what I was wondering about. So I'll tell you what, why don't I do one of these and you do the other, and we'll get the two models in place. So the number of home runs depends on the games played. So games will be your X's, home runs will be your Y's. So would love for you to try this out. I will do Barry if you can do Hank. That would be great. And so I'll just kind of talk it out up here and get right back into it. So I'm going to do a couple things. I'm going to first go to my Y equals and clear that out. And remember, guys, it's enter, view, and model. So I go back into my stat edit. And of course, I'm going to hit clear and then enter. Go up to L2 and hit clear and then enter. All right, so a lot to type in. I'll do one. So as I said, I'll do Barry. So 113. And you could pause the video for a little bit and then just eventually fast forward when I have my model in place, and when you've completed yours, that would be excellent, because it's going to take me a touch of time to put this together. So let's see if I can do that for you. So in terms of the model here, everybody, the idea would be if the person is a consistent home run hitter, then the data should be very, very linear. Remember, linear means really a constant rate of change. And so if it's really linear, then that means that the number of home runs hit over time was very consistent. There wasn't a dramatic leap or anything like that. If it's not linear, then again, that would mean that there's just some inconsistency in terms of the number of home runs hit. Okay, I'm getting a little closer on these. Hopefully I have this all taken care of here. All right, I think that's it for the number of games played. And let's get right back up here and get the home runs hit. So doing nicely. Hopefully you guys are plugging away on Hank. And we'll get that model in just a sec. Pretty amazing, just the longevity of these two baseball players, how many years they were able to play at such a high level. So let's see, 374 here, getting closer, guys. Thanks for bearing with me. And so remember the 3 steps: enter, view, and model. Sometimes, obviously, these data sets can be lengthy, but that's all right. We're doing nicely. So if I remember correctly, Babe Ruth's record was 714, and then Hank broke that in the 70s and got up to 755. And then Barry, as you can see, up to 732. Absolutely unbelievable. So let's see, let's get that in. And I've got it. All right, looks good. It's all lined up. So enter the data, view the data. And there it is. And if you kind of look, pretty linear, all things considered, maybe a little fluctuation, especially right in here. Here was the controversy time, just FYI. You know, Barry was a good home run hitter for a long time, but you can see that there seems to be a little bit of a jump right in here, at least just from my perspective. And again, what we want to do is put a model on this. So I go to Stat, I move it over to Calc, number 4 there, guys. And I'm going to go ahead and paste that into the Y1. I like doing that. It's not a necessity, but let's get that in there. And there we go. All right, so we have a model in place. I think we're ready. And we also have an R value. And again, that would be how linear the data is. And so that's looking pretty good. So let's go ahead and get this in place. I have both on my paper. The hope is that you did Hank and you've got that one taken care of. It says write a linear model for each person. Games played is the independent. Home runs be the dependent. We already took care of that. And round to 3 decimal places. So this one would be Barry right here. I'm going to put a BB for Barry Bonds. And I've got y equals 0.274 x minus 73076. There's Barry. Now I'm hoping you did the Hank one, and this is what I got when I did the Hank version of this. I got 0.244x and then minus 33.042. Okay, very good. 2 models representing the data there. And by the way, I'm going to just go back really fast while I have a moment and hit graph one more time. And notice you can see, is it perfectly linear? No. And notice here is kind of the area where I was wondering if there was going to be some inconsistency, and there is a little bit, but not all that terrible, all things considered. Okay, so let's see what else is on your paper here, just on my last screen. Let's do the slope piece and the correlation coefficient and put that together. Actually, you know what? Let's do the correlation coefficient first. So in this case, round to 4 decimal places, the correlation coefficient. And to me, this is sort of an interesting thing on how linear it is. Basically, how consistent each baseball player was hitting home runs per game. And as you can see here, basically this is Barry's correlation coefficient. Again, pretty good. And look at Hank's. I mean, look how linear that is. So in terms of consistency, it looks like Hank was probably the more consistent home run hitter from one year to the next to the next, from one game to the next to the next. So Barry had a little more of an inconsistency than Hank. Sounds good. Let's go back and talk about slope and maybe think about a different perspective in terms of who was the better home run hitter. So letter B, what does the slope in each model represent? Again, change in Y per change in X. I guess from our purposes here, I would just say it's the average number of home runs hit per game But basically, again, it's the change in the number of home runs hit or the increase in the number of home runs hit. Sorry about that. So really change in y per change in x, but this one can probably be simplified a little bit to something along those lines right there. And so if you look at Barry's slope compared to Hank's slope, it looks like Barry's slope, he hits about 0.274 home runs per game, whereas in this case Hank hits about 0.244 home runs per game. So in terms of who was the better home run hitter, well, as you can see, it looks like Barry was able to do it a little more. Okay. Let's not worry about this too much. I'll just give you the answers to this. If you kind of think about that slope as the number of home runs hit per game and then kind of flip that on its head, one home run, the way I calculated this, Barry hit a home run every 3.66 games, and Hank hit a home run about every 4.1 games. Again, don't worry about that piece. It's just something that I thought was interesting to take a look at, and I just worked with the slope in order to figure out that thing. Okay, just a very long data set there, but hopefully seeing it the second time around and putting your stuff in the calculator that you're getting better and better at it. So try a couple out on your own, and just let me know if I can troubleshoot anything on the calculator there. And hopefully, again, the three-step process is working well for you. Enter the data, view the data, and then model the data. And then obviously what we want to do is perform some mathematics with that model. All right, I'll stop that piece right here. Kind of running out of time, but as I said, please ask questions with any of the technology here. Be happy to help you with it.